Okay, in the last class we have discussed the binary phase shift key. Okay, in that symbol 0 and 1 are used and only one basis function, that is pi 1, is used. Okay, now I will move on to the next phase shift keying technique, that is quadri-phase shift keying technique. The reliable performance in the design of digital communication system is achieved by two parameters. One, a very low probability of error. The second one is the efficient utilization of the channel bandwidth. In this section, we study a bandwidth conserving modulation scheme, and this is what the bandwidth conserving modulation scheme, which is known as quadri-phase shift keying using a coherent detection, that is qpsk. As with bpsk or in the binary phase shift keying, information is about message symbols, only a message symbols, and in qpsk, which is contained in carrier phase, the phase of the carrier takes on one of four equally spaced values, that is 5 by 4, 3 5 by 4 and 5 5 by 4 and 7 5 by 4. For this set of values, we may define the transmitted signal as S1 naught t equal to square root of 2e by t cos of 2 pi fct plus 2i minus 1 into pi by 4, and up to the previous one it is same as the bpsk, and the pi the phase shift is expressed as 2i minus 1 into pi by 4, because here it has a 4 phase shifts, 0, that is 0 to end, that is 5 by 4, 3 5 by 4, 5 5 by 4 and 7 5 by 4, and this is for a complete one duration, which is shown here. T is greater than or equal to 0 and is less than or equal to t for I equals to 1, 2, 3, 4, and for the other duration or for other phases it is equal to 0, and that is shown in equation number 3.16, where what is E? E is the transmitted signal energy per symbol and T is the symbol duration. Fc is the carrier frequency, as we have discussed in the binary PSK, that is, and which is equal to Nc by capital T, where Nc is the some integer constant. Each possible values of the phase corresponds to unique die bit. This corresponds to a unique die bit. Unique die bit means it is the combination of two bits or a two symbols, 0 and a 1s, or a pair of bits which are represented in the form of gray codes, which are shown here, that is 1 0 0 0 and 0 1 and 1 1. In the binary PSK, we have used only a two symbol, and each symbol is represented by a single bit, and here we are using a pair of bits or a two bits are used to represent the quadri phase. And after this, what we have discussed is the representation of the qpsk signal and a symbol, that is quadrature phase shift keying signal and a symbol representation. Next I will move on to signal space diagram of quadri phase shift keying technique of the signals. or qpsk signals using a well-known trigonometric identity, that is what we have studied in our PU level or in the lower semesters, that is cos of a plus b. The same is applied on the equation number, this is SI equation number 3 point, the equation number 3.16, just to apply here, okay, that is this is 2 pi fct acts as a and 2I minus 1 into 5 by 4 acts as a b, that is cos of a plus b. Just to apply and expand it, we will get, that is SI of t, that is equal to, and square root of 2e by t is constant for both sides, and cos of a plus b, you can write it as cos a, cos b minus sin a, sin b. So the equation number 3.16 is expressed in cos a plus b form, that is equal to cos a, cos b minus sin a, sin b form. It is just expanded, where here I is equals to 1, 2, 3, 4. Just you put the I values 1, 2, 3, 4 and you will get the phase shift, that is 5 by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. Based on this representation, we make two observations. The first observation is there are two orthonormal basis functions. In the binary PSK, we have used only one basis function or an orthonormal basis function, and here we are using a two orthonormal basis function, which is defined by a pair of quadrature carriers, First quadrature carrier, that is phi 1 of t, or that is also called as a oscillator, that is phi 1 of t equal to square root of 2 by t cos 2 pi fct. What we have discussed in binary PSK, the same expression, the cos 2 pi fct, and here each pi are a basis functions having a unit energy, so that E equal to here 1, so this becomes square root of 2 by t cos of 2 pi fct. And the second orthonormal basis function is pi 2 of t. Similarly, it is 2 by t into sine of 2 pi fct. It has a 360 divided by 4, you will get a 90 degree, that is cos of 90, that is some a plus 90 gives the sine of that value. So you will get the quadrature phase. So that these are called as, these are differed by a 90 degree, so that which are called as the quadriphase set key, or so that it is called as the quadrature. One is the in phase and another is the quadrature phase, so that each are 90 degree phase difference, so that these are called as the quadrature carrier. And the second observation is it has 4 message points. As we have seen in the binary PSK, we have only 2 message points, that is S11 and a S12. Sorry, not S12, S21, S11 and a S21. And here there are 4 message points and which are defined in the signal vector, that is SI equal to root of E cos 2I minus 1 pi by 4, and the second one is the, and in the second row is the, another one is the opposite phase to the above, that is minus of E root E sine of 2I minus 1 pi by 4, that is opposite phase with quadrature, with a quadriphase. The quadriphase, as cos changes to sine and the plus E changes to here minus E, and where I, just you put the I equal to 1, 2, 3, 4, you will get the 2 symbols with a 4 phases, and the decision, and with the decision of the symbols or decision of the signals are decided by this signal space diagram of the QPSK system. And it has 2 decision boundaries. The first decision boundary is along the pi 1, and the second decision boundary is along the phi 2, and as I said, it has a four faces, it has a quadriface, so that it has a four regions. That is, region 1 is represented by Z1, and region 2 is represented by Z2, and region 3 is represented by, that is a message point M3, and that is Z3, and region 4 is Z4. And there are four message points, as I said, and which are represented by the gray codes, that is what 1 1, and like that is like that 1 0 first message point, and then one bit change is 0 0, and next one bit change is 0 and 1, and one more bit change is 1 1, so that the message points are 1 0 0 0 0 1 and 1 1. Okay, and sometimes this is also called as a constellation energy, and which are having the energies, that is minus e by 2, square root of e by 2, and square root of plus e by 2, and the right side and in the up and down side. And just I will show a table, which characterize the signal space of the qpsk. And in the first column, as I listed, there is input die bit. Okay, input die bit or a pair of bit symbol, and then the second column, and what is the phase saved in the qpsk signals, which is in terms of the radians, and what is the energy and what will be the message point. Those are listed in the column 3 and a column 4, and which is also based on the even and a odd numbered bits. Okay, and 1 1, okay, 1 1 of the gray code encoded bit is having a phase shift of, or represented by a phase shift of pi by 4, and SI1 with a first normal basis function, it has a positive energy, and SI2 has a positive energy, and 0 1 here 0 represents the negative and 1 represents the positive. Okay, so that SI1, the first symbol is 0, so the first signal here is negative of the energy, and the second bit is here 1, and it will be considered as the positive energy, and here both are 0 0, and here both are a negative energy. Okay, both are negative energy, means this will comes in the third quadrant, both minus minus, and 0 1 comes in the second quadrant, that is 0 1, and similarly 1 0 is represented, 1 is which is having the positive energy, and 0 is having the negative energy. So I move on to the description of this. Here the elements of the signal vectors, which are named SI1 and SI2, okay, SI1 and SI2, which are having the die bit, and which are having a phase shift of here pi by 4 as the difference. Accordingly, a qpsk signal has two-dimensional signal constellation. As we have discussed in the binary PSK, only one line we have drawn, that is n is equal to 1, and it was only two message points, that is m equal to 2, but here m equal to 4, n equal to 2, and whose phase angles increase in counterclockwise direction, as illustrated, that is shown in figure. As compared to BPSK, the QPSK signal has a minimum average energy. Just I will take a simple one example how to generate the QPSK waveform. Just I will show the figure first. Next I will move on to the explanation of this. Okay, just it consists of a input binary sequence as 0 1 1 0 1 0 and 0 0. Now group the binary sequence of input into two bits. That is, the first die bit is 0 and 1. Okay, 0 and 1, combine these two, 0 and 1, and next die bit is, that is 1 0, and the third die bit is third die bit is this one. Third die bit is 1 0, and the fourth die bit is 0 0. Now split this sequence into odd numbered sequence polarity of a coefficient SI1, the first signal, and a even numbered sequence polarity of a coefficient SI2. The first case, for the odd numbered sequence, odd number sequence or odd number sequence that will based on the changes of the the continuous same bits, the polarity will be changing in the even number that will have the negative energy. Just to go through the table of the 3.1, based on the table 3.1, we are drawing the odd number and the even number. So here SI1 will be acts as the odd number and SI2 will be acts as the even number. Based on this, based on use of these die bits, we can draw the waveform as, that is odd numbered sequence and the even numbered sequence. Just I will start with the odd numbered sequence here. Initially it has a 0 signal, and it will be 0 means it has an energy of negative, so it starts from the down, that is negative side, and it will be continued, and here 0 1, and there is no there is no continuity of the same bits here, so it will be continued. And for the next die bit, just to compare the first die bit and the second die, from the first die bit here the last bit is 1, and the next continuous of the first die bit is 1. So these two are having the same phase, but in this case the phase has to be changed. So this will be automatically changing into the positive phase, but it was representing here, then it was representing negative here, so it will be automatically changes to here positive, means 1 means here positive, and then the remaining will be continued as it is. And now come to the third die bit, that is 1 0, that is same followed, that is 0 1, and next at this point same, it is continued 1 0, and immediately after the third die bit 0, the bit starts as, that is minus. It has to actually start minus, but here it is appearing as a positive plus, so that will come down to the minus and signal will be continued. This is what odd number. Similarly, it has an opposite phase. In the otherwise, just to follow the table of the 3.1, you will understand this thing. Okay. And next, finally combining the SI1 into phi 1 of t and SI2 phi 2 of t, you will get the quadriphase scheme that is shown in the figure 3.4d. Okay, this is what one simple example to how to get the qpsk signal, just combining the odd numbered with the first basis function and even numbered with the second basis function, and that will generate the qpsk waveform. Okay, next I will move on to the generation and coherent detection of qpsk signals, how to transmit and how to detect or how to receive the signal of the qpsk. Now, as we have studied the equation number 3.17 and 17 to 19. So these are the what are the expressions we have discussed here in the above, that is 3.17 and 3. That is cos A form and cos A plus B form, and how to represent this base orthonormal base form. These are expressed in the form of the block diagram, which is shown down. That is, we may build on a 3.17 to 3.19 to construct the qpsk transmitter, which is shown in this figure. Okay, it consists of a binary data sequence, and it has a polar non-return to zero level encoder, and then which is applied to the demultiplexer, to split as even numbered and a odd numbered sequence, even numbered and a odd numbered sequence, and finally these two are added. Whatever we have discussed in the example, the same procedure is applicable here. That generates the qpsk. Okay, that generates the qpsk. The same information is given here. Okay, and the second case is to estimate of the transmitted binary signal or a transmitter. That is what the transmission. Okay, we have used the two oscillator. One is phi 1 of t and a phi 2 of t. Phi 1 of t is square root of 2 by t cos 2 pi of t, and the second one is this is the quadrature phase. And after transmitting, we need to get the received signal, and how to decide which one is the symbol which is transmitted by the transmitter. Okay, and we will consider the received signal as a x of t, and we are using the two oscillator frequencies or a two orthonormal basis functions or a two product modulator, we can say, that is phi 1 of t and a phi 2 of t, phi 1 of t and a phi 2 of t, because it has a two dimensions. First one dimension is decided by the phi 1 of t, and the second dimension is decided by the phi 2 of t, and which are given to the two correlators, here shown. That is, the first correlator is this one, and that is in phase channel, and this is the quadriphase channel. And first phi 1 of t detects the x1. Okay, and we can also say a random process of the transmitted signal of the symbol, first symbol, and x2 is the second symbol. And here we have observed in the constellation diagram, it has a two dimension, and it has a four message points and two decision boundaries here. Okay, so that we will use two decision devices with the threshold 0, one is the odd number, another is the even number, and which is based on the threshold 0. For the it is applicable whatever we have discussed in binary PSK. If is process and with expanding that, and whatever we have, that is the functional composition, and there is a pair of correlators which we have a common input x of t, that is what we have discussed, and these are multiplied by the phi 1 of t and phi 2 of t, which is shown in the block diagram already we have discussed. And here also we have used in the, as I said, that is pair of decision devices. Okay, while explaining the block diagram I have told, which act on the correlator outputs x1 and x2 by comparing the 0 threshold, and these will decides the symbols 1 and 0 based on if x1 is greater than 0, a decision is made in favor of symbol 1 for the in-phase channel output, and if it is x1 is less than 0, the decision is made in favor of symbol 0, in favor of symbol 0. This is for the in-phase channel input. Similarly, a binary phase decision is made on the quadrature channel, that is what, if x2 is greater than 0, it will made in favor of a symbol 1, and if x2 is less than 0, the decision is made in favor of a symbol 0. Next, finally, we are applying these decision to the multiplexer. This multiplexer will combine the two binary sequences produced by a pair of decision device, and which selects any one, or out of n symbols, it will select one, and which will be provided as, which will produced as an estimate of the original binary stream of the transmitter input. And next, I move on to the error probability of the qpsk. Means how much is transmitted, or whether the signal transmitted is correct, sorry, not transmitted, whether the transmitted signal is received is, it is correct, or whether it is a wrong symbol. Okay, and that is based on the receiving and the transmission of the bits. Okay, so that in a qpsk system operating on the AWGN channel, what we have discussed in the first chapter and the second chapter, while transmitting the signal, the channel adds that is additive noise, that is W of t, which will be the white Gaussian noise process, and which has a zero mean, and a for spectral density of capital N naught by 2, which is given as x of t equal to Si of t plus W of t, that is for a one complete bit duration. T is from 0 to capital T, and it has a 4 phase I equal to, this is applicable to 4 signals, I equal to 1, 2, 3, 4. And referring to the figure of the transmitter, okay, we now define the two correlator, what is x1 and what is x2 here. Okay, what is x1 and what is x1 and what is x2. Okay, x1 equal to, that is integration of whatever you have applied, that is common x of t, and which is multiplied by pi 1 of t into dt, that is equal to root of e. What is x of t, and that is and pi 1 of t, that is the product is, that is given, that is root e cos of 2i minus 1 pi by 4 plus w1, and which is, after simplification, we will get the plus or minus, that is plus or minus square root of e by 2 plus the additive noise after the transmitter, and here x2 will be the, for the quadriphase, that is integration of 0 to t x of t, and with respect to second orthonormal basis function x of t into phi 2 of t dt, that is quadrature phase, that is equal to root e sine of 2i minus 1 pi by 2 plus w2. The only difference here is this is cos and here sine, and here w1, the first additive noise, and the second additive noise, and here just to compare these two, and here that is what, plus minus, that is this is plus minus, and here minus plus, means the phase will be changing, it has an opposite phase. Okay, as we already discussed. Okay, according to the above equations 3.22 and 3.23, that is discussed, these are the correlator expressions, or the observable variables, and which are characterized by two binary PSK receivers, and which are characterized as follows, and which are having a signal energy per bit which is equal to E by 2, and has a noise spectral density equal to capital N naught by 2, and which produces the average probability of bit error in the in phase and in the quadrature paths of the coherent qpsk receiver as that is p dash equal to q into square root of e by n naught q into square root of e by n naught, and it has a 2 bits, okay, and the q function will be double than the first, that is in dpsk, so that, and here 2 is missed this, so it will becomes the q of e by n naught. Okay, as we have discussed, in the binary psk, it will be, okay, it will be 2e, and here the 2 is eliminated, that becomes the, it has a more efficient than the binary psk, and where e is written in place of eb, that is what I have discussed. Accordingly, the average probability of correct detection of the two channel paths, that is working together, are given by that is the probability of correction PC equals to 1 minus the average probability of in phase and the quadrature phase, that is P dash whole square equal to, that is 1 minus q times what is P dash, just to substitute P dash in that, and then expand it, what we will get, that is a minus b whole square formula, and simplify it as it is. And in this case, that is q square of this value will be the, for example, suppose if we take a point 0.01 square, that gives the 0.00401, and which has a very small value and which will be negligible, so that we are neglecting in this case, okay. And then the average probability of symbol error for the qpsk is defined as, that is P equal to 1 minus, that is probability of the correction of the two channels, that is P equals to 1 minus PC, okay, that is equals to that is 1 minus 1 gets cancelled, and thus this minus 2q becomes plus 2q, and plus becomes this minus, and here as I said, that is explained, that is suppose if the q that is the probability of that q function is 0.001 and it's taking the square, will gives a very small value, so that we are omitting that part, that is that gives the finally, that is probability of error will be the 2 times the q of this value, 2 times the q of this value, that is 2 times q into square root of e by n naught. And what will be the bit error rate? Bit error rate will be the, that is average of, average of the symbol, that is taking divided by 4, we will get the q of 2eb, what we have discussed, like P10, P01, and taking the average, that gives the 2eb by n naught, like that here you will get the 2eb by n naught, okay. So that I will stop this video, and I will continue the MRA PSK in the next class.